Okay, we're doing it. We're doing the everything you need to memorize video for decision one. Now, this has been a long time coming, and as you can see, there is a lot of information on here. So I'm just going to kind of preface this whole video. When I've got things to do with algorithms, it's been very hard to kind of describe how to do an algorithm. There is nothing that will replace practicing using an algorithm rather than just watching me read through it. You really do need to practice these things for them to make the most sense. And a couple of other bits. There's some things from the first chapter to do with flow diagrams and trace tables I haven't included. So, there's just a couple of bits here and there, but really I think I've covered pretty much everything that I think needs to be memorized. Trace tables and flow diagrams are pretty kind of common sense. So without further ado, we will get started. And to begin with, we remind ourselves of the sorting algorithms. And to begin with, we will remind ourselves of the bubble sort. And I'm doing it for an ascending bubble sort. Obviously, you would know how to adjust this for a descending bubble sort. So for one particular pass, you compare the first two numbers that you've got, or first two things, whether it might be alphabetical order. And if they're not ascending, you swap them over. You then compare the next two. If they're not ascending, you swap them over. And you do this until the end of the list, and that classes as one pass. You're going to repeat these passes until there are no swaps. And after there have been no swaps that have occurred through an entire pass, you can then declare the list sorted. And there's often that part as an essential part to kind of get that final mark in a bubble sort kind of question. Although usually you only have to do one or two passes. They don't typically ask you to do the whole thing. A tip that I like to use is every time I do a swap, I use a new line. It makes it much easier for me to keep track of how many swaps I've made, and also it makes it a little bit easier to count how many comparisons I have done as well. The next one we have is the quick sort, the one with the pivot. Again, I'm doing it for ascending. You can figure out what it would be if you were going to do it for a descending quick sort. You pick a pivot. I always put a circle around my pivot. People do it in different kinds of ways. Pick that as your middle value. If there's an even number, you can do middle right or middle left. The standard way is to do middle right, but the mark schemes do accept middle left as well. And then what you do is you put the values that are smaller than the pivot to the left and bigger to the right, but you must make sure you maintain their order. You don't want to actually do multiple kind of sorts. You only want to put them in the original order they were in, smaller to the left and bigger to the right. Then what you can do is you can lock in the pivot by changing it from a loop around it to a rectangle. Again, that's just my notation for doing this. But after you've locked that in, you're then going to pick more pivots, one on either side of that original pivot, and you repeat this until all of the pivots become locked in, where they have these sort of rectangles around them. And then again, at the end, you can declare the list sorted. Now, bin packing, first fit bin packing is the first kind of type. That's literally you just find the first item in the list, you put it in the first bin that it will fit in. If it doesn't fit, go to the next bin. First fit decreasing is where your original list you're going to sort into descending order first, and then you will use the first fit algorithm from there. The third kind is the full bin packing algorithm. It's not really got an algorithm at all because you have to manually look for combinations to fill the bins, and then you can just use the first fit algorithm for the other ones that are left over. Now, order is a very small part that's kind of brought up in the first part of chapter 1. Order is about like there are ways you might have to work out order. It's about how many comparisons you might need to do, that kind of stuff. If the order is of a function of n, it might be like quadratic, it might be logarithmic, it might be linear. Well, if it's f of n for n items and its duration is t seconds, if we wanted to work out its duration for m items, what we have to do for this is we would find out what the function would be with m substituted in, what the function would be with n substituted in. We'll divide them to get that kind of scaling factor, and we multiply that by the time that it should take. Next thing we do is start thinking about graphs, and people always get a bit hooked on this idea of lots of terminology. It's only ever been like a 1 or 2 marker kind of question across the whole of the D1 paper, so I wouldn't worry too much about these because there's quite a lot to remember. So a route from one vertex to another, that is a walk. And then a walk where no vertex is revisited, that is something that we call a path. A path that ends where it started is called a cycle. I think that one's kind of quite intuitive. And a cycle that visits every vertex is a very special kind of one. This is called a Hamiltonian cycle. Hamiltonian cycle. A walk where no edge is revisited, that is something that is called a trail. And a trail where every edge is visited and starts and ends at the same vertex, that is something that is called an Eulerian circuit, and that gets brought up later on when we do some things to do with route inspection. So we'll continue with the stuff from AS with some things to do with graphs, and we've got some more terminology up here. So a graph with a path between any two vertices, we would call that a connected graph. And it was kind of easier for me to show you an example that was not a connected graph. This is one single graph. It is not connected because there isn't a path connecting them together. If I added in an extra path like this, then it would be a connected graph, but at this point it's not. A graph with maximum of one edge between vertices and no loops at all is what we call a simple graph. So this example that I've got on the right is not a simple graph because between these two edges, these two vertices here and here, we have two edges. There can only be one, and I also have a loop here. So this is not a simple graph. A graph with every vertex connected to every vertex is called a complete graph. And this complete graph that we've got here, we use the letter K for it. This is K4. We have 4 vertices and every single one of them has a connection to every single other one that we've got. Graphs with the same information but shown differently, like these two here, they are called isomorphic graphs. They are called isomorphic graphs. And graphs which can be drawn with no crossing edges at all are ones that we would call planar graphs. So we can see this graph here is planar. Although there's an edge that's crossing it right now, I could take that edge between these two vertices and I could pull it around the side like this so that I no longer have any of them crossing over each other. Now, if you're doing A2, you'll know the planarity algorithm, which is based off this concept of finding a planar graph. So you start off for the planarity algorithm by finding a Hamiltonian cycle, and you use this as your outer circle. I mean, really, it's like a polygon for those bits that would be on the outside. You then add in all of the internal edges, which might be lots of lines between those sides of that kind of circle that I'm talking about. And the whole point of the planarity algorithm is to sort your internal edges, these ones here, between ones that will remain inside and ones that will move to the outside. Now, the logic of this is that if they are crossing at the setup stage, which is this stage that we're talking about here, one of them must be remaining inside and the other one will need to shift outside. So if you pick one that's in the inside and it's crossing two other lines, those two other lines or those two other edges are going to have to be labeled and go to the outside. You'll go through a kind of logic with this, and if it's not logically possible, it is not planar. It cannot be drawn as a planar graph. And obviously, if it can be done, you can draw it as a planar graph, and that's obviously one of the best ways to show that something is planar, is literally to just draw it and show that it is a planar graph. And then Euler's handshaking lemma does kind of get mentioned quite a few times, and it's quite good for solving any sort of puzzles with these graph types that we have. And that's just that the sum of the vertices degrees is the sum of, or the total number of edges multiplied by 2. So what this means is that you can never have an odd number of odd vertices. You're always going to have an even number of odd vertices because the sum of the vertices degrees always have to be the number of edges multiplied by 2. And then we move on to algorithms on graphs, and this is really where my description of these things is not going to be a replacement for actually just practicing these. So this is a good overview of all of D1, but if you're like, oh, I don't really remember that one, you need to go and practice it. This is not going to be enough of me just describing them to you. So for algorithms on graphs, the first one is about finding minimum spanning trees. You should know what a minimum spanning tree is, so I haven't defined that here. And we have Kruskal's algorithm, which I said in the notes is a bit like chaotic, K for chaotic, because it may only form a tree at the end. It might not look like it's growing neatly like a tree, so it can be quite a chaotic kind of algorithm. And the tip for this one is to order all of your edges first from smallest to biggest, and you're going to just add all of the smallest edges on. That's your number one priority, is to use the smallest edges. The second priority is that it must remain a tree. You don't want to add a smallest edge that creates a cycle, because if it creates a cycle, it's not a tree anymore. And then the third thing you need to make sure that happens is that it includes every vertex. Now, what you should show for this is you should show which ones you accept and which ones you reject. The main thing is just which ones you accept. The rejection isn't as important because that's implied by which ones you are accepting. Now, the other kind of algorithm is Prim's algorithm, and I remember this one because it's kind of neat or prim and proper, meaning that it kind of forms a tree immediately. It kind of grows as a tree, whereas Kruskal's one kind of goes all over the place. So that's how I remember Prim's. Now, the difference with Kruskal's and Prim's is that the priority for Prim's algorithm is that it must be a tree. So you're always trying to add the smallest edges, but you can only add a small edge if it will contribute to the growth of that minimum spanning tree. degree. And obviously we're going to stop any cycles happening. And obviously we have to make sure that we've included every vertex. Now the priority of using prims is it's actually really easy to do from a graph, because you don't have, it's just so simple to spot which is the one I should be using next. Whereas cruscals, you want to sort of write all of the edges down and order them. So often prims can be quicker. The way that you kind of communicate how you did prims was you would write down the order of the edges that you accept. So the order that you write them down is really important, and the examiner will expect to see those as a list. And of course, you need to ensure that you can do prims on a distance matrix as well as from a graph. And that is something that I'm not going to be able to demonstrate on this document. So it's something that you're going to go and have to look at from your notes and just do a couple of practice questions. Right, now the next part that we have here is finding shortest paths. Now the first one is Dijkstra's one that we have. Now again, this is not going to be one that can be demonstrated very easily, but I'm going to give you a bit of a logic and what it does. So Dijkstra's algorithm, it is finding the shortest path from a single start point. So I want you to practice using them. It is far better than remembering instructions, but the general gist of what we do with Dijkstra's is we're tracking the distances, labeling when you have a guaranteed shortest path. So you find all of the different pathways that can get you to a particular point. Once you know you found the shortest way to that point, you'll record it, you'll keep track of that distance that got you there, and then you'll start finding more shortest distances from that point. That should make sense if you've done this. This is not a teaching tool, this is a revision tool. Now, Floyd's algorithm is only in A2. Again, you need to practice this. The difference between Dijkstra's and Floyd's is that Dijkstra's will only find the shortest path from a single start point, whereas Floyd's will find the shortest path between any pair of points that we have, okay? So you're going to practice it. This is the one where there's one table to track the distances and the other one to track the via kind of routes. It might be quicker to go like, I don't know, via B, or it might be quicker to go via B then C instead of going direct to it. So hopefully that will remind you of what I mean for Floyd's one. And sort of the general sort of approach that we take for this is that you're checking if going via another vertex reduces the distance. And if it does, you record that in there. Now, route inspection. Route inspection is actually only is in AS, but part of it is in A2, and I'll kind of explain that as well as we go. Now, route inspection is all about trying to find the shortest route to travel along all of the edges and return to the start. Sometimes they will change this part about returning to the start, which I will cover in just a second. Now, for Eulerian graphs, this is where we have all of the vertices that have an even degree. The shortest route that we have here, this is what I'm trying to say, the shortest route to travel along all of the edges and return to the start, it is literally just going to be the total weight of the network. It is the total weight of the network. Because in an Eulerian graph, you literally can just trace all of them and get back to the start, and you don't have to repeat any of them. Now, if you have a semi-Eulerian graph where exactly two of them have an odd degree, exactly two of the vertices have an odd degree, the shortest route is going to be the total weight plus the shortest distance between those odd vertices. So it is going to be the total weight plus the shortest distance between the odd vertices. Now, if we have something with 4 odd vertices, it is going to be the total weight, again, and this time it will be the shortest distances plus the shortest distances of the 2 pairings of the odd vertices. So you have 4 vertices, you find all of the different pairings that you can come up with and that uses all 4 of the vertices, and you'll pick the pairs where there are 2 pairs that has the shortest distance in total, and that gets added on. Now, if you can start and end anywhere, this changes the problem. So what you would choose to do here is you would choose to start and end at the odd vertices, and what this does is it collapses a problem down, which is a semi-Eulerian graph. It collapses it so that it goes down to just a normal Eulerian one, meaning it's just the total weight of the network. If it's 4 odd vertices, it collapses the problem down to a semi, and if there are 6 odd vertices, it collapses it down to a 4 odd vertices. This bit where there are 6 odd vertices, that's usually reserved for A2, but it does just become a 4 odd vertices instead. And again, this is all explored in more detail in my videos that cover all of this stuff to do with route inspection. Now, the next part is only in A2. It is the traveling salesman problem. Now, this is a bit different to the route inspection. Route inspection was the shortest route to travel along all of the edges and return to the start. The traveling salesman problem is the shortest route visiting every vertex and returning to the start. Now, the classical traveling salesman problem is where each vertex is visited once, exactly once, whereas the practical traveling salesman problem is where each vertex is visited at least once, where it doesn't matter if you go back to a vertex. Now, the way you do this is you're about finding the upper bounds and the lower bounds, and you try and kind of sandwich in between where we think our solution would be. We try and get a small range between a lower bound and an upper bound. And there are 2 ways of creating upper bounds, and then there's one way that we use to find a lower bound. So one of the ways that we use to find an upper bound is using MSTs, which are minimum spanning trees. Now, the initial upper bound is found by taking the weight of the minimum spanning tree weight, and multiplying that by 2, because that connects all of them together and you're retracing all of the paths, which means you go back to the beginning and all of the vertices are visited. But this is a solution, but it's not a very good solution. So we can reduce this upper bound by adding in shortcuts that might save us some time. And often those shortcuts, there's not really an algorithm for that. It's just about spotting where you could change something in your minimum spanning tree to be able to sort of save some time or distance. The second method is the nearest neighbor algorithm. It's an easy algorithm because it kind of just describes what it is in the title. What it does is it finds a Hamiltonian cycle, which is a solution, but it is not necessarily an optimal solution. So it is a solution, but it's not necessarily optimal. The way this works is you pick a vertex, you find its nearest neighbor, and then you find that one's nearest neighbor, and you find that one's nearest neighbor, etc. And this generates a Hamiltonian cycle. You repeat this for all of the vertices to come up with lots of different Hamiltonian cycles, and then all you need to do is select the lowest weight of all of those ones that we've just generated as the upper bound. Remember, we want our upper bound to be as low as possible, and we want our lower bound to be as high as possible. So these all come together within one question typically. Now, for lower bounds, the lower bounds don't usually represent solutions. If it does represent a solution, then it is an optimal solution. What I mean by a solution is that it gives you a journey where all of the things are visited and it gets back to the start. Sometimes it doesn't even produce that. Now, the way you do this particular lower bound approach is what you do is you remove a vertex and its edges. You then find the residual MST, the RMST, using prims. So you're not quite finding it of the whole thing. It's just a minimum spanning tree of the total network minus 1 vertex. And then you reconnect that removed vertex with its 2 shortest edges. And so this then gives us that the lower bound becomes the weight of that residual minimum spanning tree plus those 2 shortest edges that we've got there. Again, this is all going to feel very abstract unless you're doing this alongside a bit of practice that goes with this one. This is totally different to the other documents I've done on everything to memorize. This one really needs to be done with some practice. What you do is you repeat this process of removing one of the vertices at a time, and out of all of these different lower bounds you will select the highest one for the lower bound, so that we're trying to sandwich our solution in between the upper bound and the lower bound. Okay, the next thing we're going to do is the last chapter from decision 1, which is critical path analysis, and then I'm going to do this long part over here, all for linear programming, because that's probably the biggest part which we will finish with. So critical path analysis starts off with activity networks. And now an activity network, what it does is it shows you about the activity precedence. You have to be prepared to swap edges and to redraw these when you're trying to draw your own activity network. You must only use one straight edge between nodes, which means that you may need to use dummy activities to show some precedence. I really would recommend just practicing some of these. This won't be enough in terms of just revision for it. In terms of early and late event times that you might need to add onto an activity network, when you do a forward pass, this is when you're adding times on and you're doing it from the source to the sink. What this does when you're doing a forward pass is it finds the early times, and it's always done by adding things on. What you're going to do at each of these times, you're going to be finding the largest event time at each node, because the largest event time will represent the earliest that we can sort of arrive at that particular node. When you do a backwards pass, that's the one where you're subtracting things, and you're subtracting things from the sink to the source, and this will find the late times that go on the bottom of those two boxes. This time you're going to be selecting the smallest of those different times at each node, and they will represent those smallest times. The smallest one at each of those nodes will represent the late times. Now, once you have an activity network that has got all of the early and late event times on it, they may ask you about critical activities and critical paths. In order for there to be, if there is, a critical path, the thing that will be true at each node is that the early time will be equal to the late time. So if the early time is equal to the late time, we should be able to form a path where there's only early and late times being equal to each other, and that should be a critical path. However, an activity which is connecting critical events isn't always critical. And again, you might want to go to your notes to see what I mean by this, but I just wanted to point that out. That is something that is worth looking out for when you're doing critical activities and critical paths. The float is found by taking the latest that the event can finish, you take away the earliest when it can start, and you also take away its duration. The float is almost saying, like, how much wiggle room do we have for this particular event? So we have this this activity A, which has got a duration of 4. The earliest it can start at 7, and it needs to finish by 12. So the amount of wiggle room that we have is the latest finish time, which is 12, the earliest start time, and it takes 4. 7 take away 12, take away 4, is 1, which means that we have a float of 1, meaning it could either kind of start or finish like an hour later, and it would still get done in time. Now, all of this information can be represented on Gantt charts, resource histograms, which is only in A2, and scheduling diagrams, which is only in A2. And you need to go and see the notes for these topics, because to try and explain like all of these things without much diagram space, it just doesn't really make sense at all. So do make sure that you go and have a look at the resource histograms and scheduling diagrams, because they don't really have algorithms, but they've got a bit of logic and stuff that goes with them as well. They're not that complicated. Okay, we're on the last part, linear programming. Chapter, I think it's chapter 6, is the graphical method, and then the simplex algorithm, which is the next chapter, is only in A2. So for the AS stuff, the graphical method of linear programming, you obviously draw all of your inequalities using sort of solid lines for the greater than or equal to's or less than or equal to's, and dotted lines for just less than or greater than. And then that feasible region is left as sort of the unshaded area. And we've got a couple of different approaches here. We've got one where we can see which vertex maximizes or minimizes the objective function. You may remember like the ruler method for that kind of thing. And the other one is about doing vertex testing, which is basically where you substitute different vertices of the feasible region into your objective function, and you see which maximizes or minimizes it. And again, there's things where some of the problems may only use integers for your solutions, so you just have to test lots of different values to see what works. Now we're on to the last bit, which is the simplex algorithm, and I would say this is definitely the most challenging part of A-level decision that we've got. So the simplex algorithm, the first thing that we need to do is change our inequalities to equalities, because it only works for equalities, and we use slack variables when we have inequalities that are like this, and we use surplus variables for inequalities that are sort of greater than or equal to. When we have surplus variables, that will mean that we have to use the two-stage simplex method. So if we just have slack variables, we can just use the straightforward algorithm. This is how the algorithm works for the simplex method. You take the most negative value in the objective row, and that is going to become the location of the pivot column. Then what you do is you find the smallest positive value of theta. It has to be the smallest one, and it cannot be negative. Theta is found by taking the value which is in the final column and dividing it by the value that is in the pivot column. Where the location of that smallest positive theta is, that will become your pivot row. Then you actually know where the pivot is, because there's a column and a row that cross over, and we make the value of that pivot 1, and we do that by division. We then replace the basic variable in the pivot, and the basic variable in the pivot row is where we replace the basic variable, and it gets replaced with the variable from the pivot column. So we have something where there's like this. We take the thing from the pivot column and it replaces the basic variable which is in the pivot row. Okay. This is what I mean by the pivot row and the pivot column. Here is the pivot right here. So that's why this variable is going to replace this part. Okay, so we're nearly there. Then using row operations, you make all of the other values in the pivot column 0. All of these little instructions are going to make much more sense when you have a look at it with a table, a simplex table. Then what you're going to do is you're going to check for negatives in the objective row. If they are all non-negative, then you have found an optimal solution. If they are not all non-negative, you have to repeat with the most negative one and do this whole process again. It can be very, very time consuming. Okay, we are now going to just talk about what happens if you need to minimize something, because the simplex does maximizing. So with minimizing something, you're going to start off by negating the objective function, and then you continue with the maximizing approach that we've got from the simplex method. Now, the two-stage simplex method, this is always required for where you have any of your constraints, any of your inequalities that have surplus. So when that's coming from these greater than or equal to's. What we do here is we rewrite them with the surplus and artificial variables that we've got. So they need to get written with surplus and artificial variables. So this would be done like x plus y being greater than or equal to 8. We would rewrite this as an x plus y. We would subtract the surplus and add in an artificial variable. And now we can change it from an inequality to an equal sign like this. Then the next thing we do is we have to find a new objective function, which we usually use the letter I for, and we use that new objective function to minimize the sum of the artificial variables. The sum of the artificial variables. And we do this, and then after you're using that to minimize the sum of the artificial variables, which is this kind of thing that we've got here. Then, using substitution, you need to change this objective function, which is minimizing the sum of the artificial variables, so that it is only in terms of x, y, s1, s2. It cannot be in terms of any of the artificial variables. It just doesn't work. And then stage 1 of this two-stage method is to solve this new objective function using the simplex method. If the sum of the artificial variables is not 0, there is no feasible solution. If the sum is equal to 0, in other words, these artificial variables have gone to 0, we can move to stage 2. With stage 2, you can use the basic feasible solution from stage 1 as the starting point for the second simplex that you have to go through, which is very, very long process. So basically, if they are equal to 0, that represents a basic feasible solution, and you can continue with that part to do one more simplex method process, and that should find your optimal solution. And then with the last part of this is the big M method. Now, as before, you need to rewrite all of your constraints with surplus and artificial and slack and all of that stuff. And then this time we don't do the objective function like we did here with I being equal to this. We modify our objective function by subtracting m lots of the sum of the artificial variables. And you should remember, m is just representing an arbitrarily large number. So in other words, if we're subtracting that, we're trying to sort of force these things to become 0 here. Okay, then all we need to do is perform the simplex algorithm once for this big M method. It doesn't need to be formed twice like with the two-stage parts. And we treat m as just a very large number. A few notes for this is that in order for there to be a feasible solution, the sum of these artificial variables must be 0. We also need to note that the artificial ones are going to start as the basic variables. And as before, the I part, the objective function that has been modified, must not have any artificial variables in it like we did before. So I'm talking about this part here, the I, the objective function must only be in terms of x, y, slack, and surplus. So we have to do a bit of rearranging and substitution for that. That was pretty tough. So this is everything that you need to memorize for D1. So please make sure that you are doing this alongside practice with different questions, because this is not going to be enough by itself, whereas the other documents that I've done usually are. So good luck with all of your revision for this. I hope that your exams go really well, and I will hope to see you in another video soon.